Okay, so last class we learned about redox reactions. We learned about a lot of stuff, but redox reactions was one of the reaction types that we learned about. We can classify things as being oxidized or reduced based on a couple of different factors. So one of those factors, the last factor that we learned about, was oxidation states. We had a set of rules for figuring out what the oxidation states are, and then we can assign them to things in a problem like we did for this problem. And one of our definitions for oxidation states is the oxidation number increases. One of our other ones is that we lose electrons. So Leo the lion goes grr, losing electrons is oxidation, gaining electrons is reduction. Reduction also in our oxidation state definition, like for nitrogen here, our oxidation state number for nitrogen went from +5 to +4, number go down, number gets reduced, so does that element. So nitrogen in this reaction was reduced because the oxidation number was reduced. That also implies that it maybe lost some electron or gained some electron density. Other definitions that we have are based on oxygen. If you gain oxygen, that's oxidation. If you lose oxygen, that's reduction. That would be one other way of classifying it, but typically we can just use oxidation states or our electron definitions instead. Going along with things getting oxidized and reduced, both of those things have to happen together. If we're thinking about the transfer of electrons for oxidation and reduction, if I'm transferring electron to something, if I'm transferring money to somewhere, right? If I'm transferring money, it has to go somewhere. Somebody has to receive that money. It doesn't go into the void. Electrons are the same way. If an electron is lost, that means that it must have been gained somewhere. It's not just roaming free in the world. It'll get picked up by something. So the reactant that reduces an element that causes the reduction of another thing is the reducing agent. The reducing agent causes reduction. The reducing agent is also the thing that is oxidized. On the other side of the coin, the reactant that oxidizes another element or causes oxidation in another element is our oxidizing agent. So the oxidizing agent causes oxidation. Oxidation is losing electrons. If it's causing something else to lose electrons, that means that it's gaining electrons. So the oxidizing agent is the thing that is reduced. Okay, so let's identify some redox reactions, oxidizing agents, and reducing agents. We want to determine whether or not each of these reactions is a redox reaction. For any redox reactions, we want to identify the oxidizing agent and the reducing agent. So for our first one, we've got lithium metal reacting with chlorine gas to form lithium chloride. Our rule for neutral compounds, in their natural state, the oxidation number is 0. So lithium and chlorine gas both get oxidation numbers of 0. In an ionic compound, the chemicals get their charge, or the same number as their charge. It's not the same thing, but it's the same number. So lithium forms a 1+ charge, so it's going to get a 1+ oxidation number. Chlorine, as chloride, has a 1- charge, so it's going to get a -1 oxidation state. Which of these two was oxidized? Was it lithium or was it chlorine? Alternatively, which of these two was reduced? Chlorine. Chlorine was reduced. Chlorine was reduced because the number went down. So it went from 0 to -1. Cl was reduced. What caused Cl to get reduced? The lithium. The lithium caused it to be reduced. So lithium is the reducing agent. And then we also have the opposite that's true. So since chlorine was reduced, lithium was oxidized. Our definition for oxidation, that the oxidation number went up. So lithium was oxidized. What caused lithium to be oxidized? What caused lithium to lose its electron? The chlorine. So chlorine is the oxidizing agent. This concept has similar vibes, at least to me, as when we talk about acids and bases, for those of you that remember acid-base conjugate pairs, conjugate acid-base pairs. This has similar vibes to that, to me, at least. Any questions about 1? All right, 2, we've got this reaction between aluminum and tin. So aluminum is in its normal natural state as aluminum metal. On the right side, tin is also in its normal natural state. So it gets a 0 for its oxidation number. And then for ions, like our tin 2+, our stannous ion, and our aluminum ion, the number of the charge is the same as the oxidation state number. So tin gets a 2+, or a +2, aluminum gets a +3. Did we have things that changed their oxidation number from the left side, the reactant side, to the product side, the right side? We sure did. So aluminum went from a 0 to a +3. That means that aluminum was oxidized. Tin is the other thing that's in there. Tin went from a +2 to a 0, so tin was reduced. The oxidation state number went down. And then the opposite thing is the thing that caused that. So tin caused the oxidation. So tin is our oxidizing agent. Tin was reduced, so it's the oxidizing agent. Aluminum was oxidized, so it's the reducing agent. Okay, and then we've got lead 2 nitrate reacting with lithium chloride to form lead 2 chloride and lithium nitrate for our third one. So we've got ionic compounds. Their charges are going to be the same as in their charge numbers. So our lead here is going to be a +2. Our lead on the right side is also a +2. In lithium chloride, we get a +1, -1. On the product side, chloride's a -1 still. Lithium's a +1. And now the only piece that we have to pick apart is our nitrate. Our nitrate is overall a 1- charge. The oxidation state numbers inside of our nitrate have to add up to a -1. And since we've got some things that show up that are nonmetals, we would refer to our nonmetal hierarchy list where fluorine's at the top, it gets a -1. If we've got no fluorine, proceed to hydrogen, which gets a +1. proceed to oxygen, which gets a -2. Then our halogens get a -1. Our oxygen group gets -2. Our nitrogen group gets -3. So oxygen shows up before our nitrogen. So oxygen gets its preferred -2. That's going to be true on the right side as well, because it's the same nitrate group. We've got a total of -6 from our oxygens, plus whatever our nitrogen has, and that has to equal a -1. So X, whatever our nitrogen is, has to be a +5. Is this a redox reaction? No, it's not a redox reaction because none of our things change their oxidation state moving from the left to the right. So our lead was a +2. On the right side, it's still a +2. Our nitrogen was a +5. On the right side, it's a +5. Our oxygen was a -2, still a -2. Lithium was a +1, still a +1. Chloride was a -1, still a -1. So this was not a redox reaction. And then our last one, we've got carbon in its normal natural state. So we give that a 0. We've got oxygen in its normal natural state of being O2. So that gets a 0. And then we've got a molecular compound where we've got carbon and oxygen. Oxygen shows up on our list. It's the third entry from the top. It gets its preferred -2. To balance that out, we need to give our carbon a +4. So carbon went from 0 to +4. Its oxidation number went up. So carbon was oxidized. That means that oxygen is the oxidizing agent, which shouldn't be surprising because that's like it's named after that. Although I think sometimes it's the reducing agent, so it's not all the time. And then oxygen went from a 0 oxidation state to a -2, which is a reduction in oxidation state number. So oxygen was reduced. The thing that caused that was the carbon. So carbon is the reducing agent. Questions about any of those or any of our rules? Very fun, very cool rules. Okay, we also have what we'll touch on very briefly, an activity series. The activity series predicts whether a redox reaction is spontaneous. This is something that you'll go into depth in Chem 2. For now, though, we're just learning it as like this is a trend. So the activity series generally talks about the tendency to lose electrons. So magnesium has a greater tendency to lose electrons than copper does. It's more likely to give away its electrons. So if you have a reaction between Mg, magnesium metal, where it has all of its electrons, and copper as an ion, where it doesn't have all of its electrons, copper actually wants those electrons more than magnesium does, and so it'll change electrons with magnesium. So if you put a magnesium strip into some copper 2+ solution, some cupric solution, you will end up with this reaction that occurs. You'll get solid copper that plates out onto the magnesium strip, and that blue color fades because of the copper being pulled out of solution. The reverse reaction does not occur. So if you swap it so that it's magnesium ion instead of magnesium metal, and it's copper metal instead of copper ion, the copper stays perfectly intact inside of the magnesium solution. So it doesn't run both ways. One of these directions, it's spontaneous. It occurs without you having to put in extra energy. It wants to do that. And the other direction, it will not. You would have to put in extra energy for it to go through with plating out your magnesium onto the copper strip. So the activity series of metals lists metals in order of decreasing tendency to lose electrons. Each of these reactions is an oxidation half reaction. If you write them in the reverse direction, then it becomes a reduction half reaction. We can see those here. So the way that the activity series works, like the very bare bones of it, is that any reaction on the list is spontaneous when it's paired with the reverse of something below it. So for example, lithium with lithium plus E minus, that's the one that's the top of the list. Very eager to give up its electrons, lithium is. If we pair that with the reverse of something below it, like zinc 2 plus 2 electrons going to zinc metal, if you combine these two reactions together, that's a spontaneous reaction. It will occur without putting extra energy in. If you were to flip the directions, it's not spontaneous. And the way that the whole table is listed, the things at the top are the most reactive, they're the most easily oxidized, they have the strongest tendency to lose electrons, they're very eager to give up their electrons. Notice that lithium, all the way in the top left of our periodic table under hydrogen, all the way up here, it's our most reactive. It's an alkali metal. We know that the alkali metals are very reactive. A bunch of other things kind of in that general vicinity are also fairly reactive. Potassium's quite reactive. We're missing a couple of things, but our alkali metal is very reactive up there. And then things on the bottom, things that are not reactive. There's reasons that we wear silver and gold jewelry. It's because they're not reactive. So that's why we see these on the bottom. They like to stay as their solid form. They don't like to go to their ion form. So those are maybe some things that you could cue into your brain to remember. Really reactive stuff up at the top, like lithium. Lithium, if you drop it in water, reacts, like fizzes and stuff. Gold and silver, not very reactive. Okay, so which of these metals is most easily oxidized? Sodium, chromium, gold. What is oxidizing? Losing electrons. Losing electrons. If we look at our activity series and we look for sodium, chromium, gold, we just talked about how gold's very non-reactive. These are all set up in their oxidation half reaction form. So gold is at the bottom, the least likely to form an ion. Chromium here in the middle, moderately likely to lose electrons. And sodium way up close to the top, very likely to lose electrons. So sodium is most easily oxidized. It's highest on the activity series. And then last but not least, determine whether each of these redox reactions is spontaneous. We've got zinc in both cases. So zinc being oxidized, and then nickel or calcium being reduced, gaining the electrons from the zinc. So zinc in the oxidation direction, and then we've got nickel and calcium in the opposite. So let's look at our table. Here we've got zinc, and we had calcium in the reverse, and we also had nickel in the reverse. And I'm hoping that it was this nickel, because some of the transition metals have like different activity series entries depending on where they are. Okay, so zinc in the forward direction, and then we had the reverse of this nickel, we had the reverse of this calcium. Which of those is going to be spontaneous? Which pairing? Zinc and nickel or zinc and calcium? It's zinc and nickel. Nickel is below zinc, and it's flipped. Any half reaction on the list is spontaneous. It happens by itself when it's paired with the reverse of a half reaction below it. So zinc and then the flipped version of this nickel will be reactive or be spontaneous. That's about as complicated of a question as you might expect to see on an exam. You don't have to have the activity series memorized, but you won't, if you're given a question with the activity series, you won't be given like the cues. You also might not be shown that it's going in the oxidation direction. You might just have to, you might just get like this little sliver of metals kind of on the side question.
It's always determined by the first element mentioned that's given that?
So you would just look at, okay, what are my two things that I've got? Figure out which one's going in the forward direction, which one's going in the reverse direction, and how are they related to each other. If the forward one is on top on the activity series and the reverse one's below it, that will be spontaneous. If it's the reverse that's above and the forward one that's below, it will not be spontaneous. So it's just this paragraph. So zinc forward direction is above, reverse of nickel. And B is not spontaneous, it's not fun, it's not quirky, because calcium is above zinc. On the activity series. Again, this will be covered more in depth in Chem 2 if you go on to take Chem 2. Otherwise, this is, I think, all the treatment that we'll get for the activity series. Other questions about the chapter? Redox, reactions, titrations, acid-base? Yes? Sure, so seeing if something's reversed, we're looking at what's over here on the left side. So our oxidation or activity series always has the solid form, the neutral form on the left side, the positive form on the right side. So if we wanted to, we could break these out. So zinc is going to zinc 2+, or zinc ion. Nickel is going from nickel 2+, or the nickel ion, to nickel as a metal, neutral metal. So we're looking for, do we have either of these? And on our activity series, we have zinc going to zinc 2+. The electrons are not shown. The transfer of the electrons is implied. And we'll talk about that more in our little extra bit about redox reactions. So this was the same direction, this is the forward direction. For our nickel, nickel went from 2+ to nickel neutral metal, which is the opposite of the way that it's laid out in the table. So that's why it's the reverse. And we'll stop there.